So how do we use the sine and cosine functions to approximate our known function f of x? So we seek gn of x, which is our approximate function, which will be a0 over 2 plus a sum over sine and cosine functions weighted by coefficients a and b. But how do we find these coefficients a and b for the cosine and the sine functions? Actually, we seek them by minimizing the difference between the function f of x and gn of x. That makes sense, and we'll actually minimize this difference using the so-called least square method. And without showing the derivation, this leads to the following definition for the coefficients. So ak here is defined as integrals that are containing multiplications of f of x and the cosine basis functions, and equivalently for the bk, which will be integrals over f of x multiplying the sine functions. This is like basically a projection of the basis functions onto our function f of x. And actually we also see that a0 is simply the arithmetic average of our function f of x in the interval defined. We will use actually usually an interval of length 2 pi, either from minus pi to pi or from 0 to 2 pi, but this can be entirely relaxed. That's not a constraint. What is very important is we always assume that our function is periodic. So even if we say f of x is defined in a certain interval, it actually means it's going to be periodic from minus to plus infinity. Every limited function in space can be made periodic. So let's make an example. We try to approximate a function in an interval. We take the interval 0 to 2 pi. Again, that's arbitrary. It could be any interval. But just as is indicated here in the graph, defining to approximate a function here basically implies that it's periodic from minus to plus infinity. So as a function, we use x squared. F of x equal x squared, and you see it here defined in the interval 0 to 2 pi. So what we need to do now is to find the approximate function gn of x. The equation is again given here, which is a0 divided by 2 plus a sum over weighted sine and cosine terms. So now how to calculate the coefficients ak and bk? Well, we know the equations for them. The integrals over, for example, f of x multiplying the cosine or sine function. Let's start. Here's an example. Let's calculate a0. a0 will be calculated by calculating the integral over the function itself over the whole interval. We said before this is the actual arithmetic average, and here is the solution to that. And we continue basically with a1 and then b1, b2, and b3, and this is left as an exercise. What is really nice in many cases is that the actual function gn of x can be given in closed form. And that's shown here. So this is basically the approximation of our function f of x as a function now of how many terms we use in this approximation, which is described by the capital N. Now let's look at this graphically. So what you see here behind me is in red you see the interval where we're actually trying to approximate that function, and with progressive n. Of course we are getting better and better with our approximation, but now something interesting is happening. You can see this, and in the next step we'll actually focus at the edge at the right hand side where we in fact have a step from one interval to the other. If we zoom in there, you can see that we're actually, even if we add more and more terms, we're not approximating the function very well at the edges, actually overshooting. And many of you probably know this is the famous Gibb's phenomenon, which actually cannot be avoided. which is an overshoot that we have at if we approximate a function with a discontinuity. Actually, we cannot get rid of this. Even though if you want, the error between the approximate function and the true function is converging if n goes to infinity, that overshoot will never go away. That's actually an indication that if we use this so-called spectral method, we should always kind of avoid having discontinuities in our functions that we want to approximate. So this is kind of a worst case scenario. So this is something we have to look out for.